Hello everyone, welcome to part 2 of our video number 5 about calibration of the Danube watershed. As I said before, in this project we took a small watershed in the Danube Basin, which was part of our previous European project and also part of our Black Sea project. I'm not going to cover much details about these two projects. If you are interested, you can see more detail in the two papers listed here. In the previous video, I showed you some pre-calibration steps, and I'm just going to go quickly through these here. The first pre-calibration step was to plot and check the precipitation and discharge data to make sure that they are correct. And I did that for every discharge station and also every climate station, rainfall especially station, and they are all fine. I mean, there were some problems initially in the European project, but we had corrected all the anomalies in the previous project. So for this project, they are all fine. And then I said we use the map option to get a feeling for the watershed that you are calibrating. In order to create the map project, the first thing we have to do is to build our SWAT-CUP project. So let me just do that and quickly build the Danube project in SWAT-CUP. All right, so I'm going to use SWAT-CUP Premium, but it will be the same if you use SWAT-CUP 2019. All right, so we start here and we build a new project. Next, the first thing I'm asked for is the texting out location. So my project is in ArcSWAT projects and the Danube project, then scenarios, default, and texting out is highlighted. Before I click on this texting out, what I'm going to do is I'm going to delete when you build the project in ArcSWAT and you run it, which you should do to make sure that you at the end the SWAT runs. The SWAT is going to put all the outputs in texting out. So if I go to my texting out, you see all the outputs are here. And often these are large files, and when we make a SWAT-CUP project, we're going to copy this folder twice. So in order to avoid copying unnecessary files, I'm just first going to delete all these output files, because in here at this point we don't need them. So, and then I can click on texting out, open, and next I'm asked what kind of project I want to run. In SWAT-CUP Premium we have SPE, which is similar to SUFI 2 before, and PSO, and I use SPE here, and then it wants the project name, so I just call it test Danube, and this will get added to it automatically, and it says where do I want to copy the project. I copy it always in the same location as my ArcSWAT project. So in here, Danube project, copy it in here. So what happened is that I now have in the Danube project, I have a test Danube, and in here I have the backup, which is my texting out basically, and then I have a whole bunch of folders which I have explained all of these in previous videos, so I'm not going to spend too much time here. But here is where my project is. Okay, so the project is created. I just want to look at the maps now. I will come back later to fill in the input files. So I can already go to maps and outlet map. That will bring the Bing map up, and then I need to go and import my outlets, and the outlets reside in my project, SWATCUP ArcSWAT project. Here is the SWAT project. Here is the Danube project. And I have to go into the watershed and look for the shape files, right? Yeah, I should look for the shape files. Okay. So what this does is to create these GeoJSON files, which then I can drag into my map and visualize the watershed. Okay, so what happened now is that in my SWATCUP project, I have now a folder called ArcSWAT. In ArcSWAT is the shape folder and also the GeoJSON folder, which has all the information I need to visualize the watershed. So if I drag the subbasin into this map, I can see the subbasin. But another probably better option would be to go to internet and use our website www.2w2e.net. And here you can see a better version of the Bing map. And then you can open that folder and drag your maps into here. So here you have, you can better maneuver in this map. So we see the watershed here, and I can bring in the river, which I'm interested in the river. Here are the rivers, and I can also bring in already the outlets or the monitoring stations, so I can now visualize the area. So you can see right away that there is this snow mountains here, the Alps. And then if I go deep inside and have a look at how well the rivers are simulated, I can see that, okay, here is the upstream, starts from the snowy mountains, and the river goes down. This is the actual river, and that's my SWAT river, the blue line, so it is not so bad down here. But when I go, the things that I notice is that there are urban areas, there is a lot of forested areas, and the river, of course, Danube is a large river and it's used quite heavily. And if I go further, I can see that there are dams, there are reservoirs. Here, the river going through residential area. There is a lot of water control on the river. But basically, the river is generated in ArcSWAT quite well. Sometimes if it doesn't, it's because the resolution of the DEM is not very good, or you don't have a burning. If you have a burning river, then that would be a better option. So here I see some strange things. There is a river going here. There is the actual river going down here. There is a river going through here. So I don't really know what these are. So there are some mistakes in simulating the rivers in ArcSWAT. And then if you go down, so you can go down the river and see all the water control here. You see there are controls, but the problem area is usually the flat part of the, this side is okay, it's the flat part of the watershed that the river usually deviates from the actual river, but that is expected. And I had noticed before there are some complexities here, the town, and there are a lot of storages. Now, I don't know if I can find them all, but I noticed there is a lot of reservoir and ponds that to store water and so on. So you can get a good feeling for the watershed here, and the fact that there are many residential areas and agricultural areas, so you know that there is a lot of water being taken out of the river. There is a lot of water being put into the river from the water treatment plants, and there are some big deviations. This is what SWAT does. This is where the river is, so it's not an ideal situation when it comes to simulating the rivers. But okay, in general, I mean, it is not so bad. So that is what we have. So again, some bridges and water controls and so on. So there are a lot of things going on in this watershed. So what I learned from this is that the highly agricultural area, so there are irrigations and so on, there is water control, and there are bridges and dams. So you should not expect always the perfect simulation. So I should expect there is some discrepancies between the peaks, the simulated peaks and the measured peaks and so on. So you have to keep the reality in mind. All right, so I have looked at the watershed and I have some idea what's going on here. I can go back to my PowerPoint, and yeah, here I mentioned that you can go to www.2w2e.net to get a better visualization of your watershed. Some of the pictures I have copied here to show some of the problems, the deviation between the simulated and actual river, and then some of the dams and reservoirs that are on the river. And here is a big reservoir. And so when you have, and there are ponds and water storages, so when you have a dam like this, you can really not simulate downstream of the dam very well unless you give SWAT the dam operation and the discharge from the dam. In that case, either I not consider that outlet which is right after the dam, or that yeah, I try to find some information to provide SWAT with the management of the dam. And so here are some of the discrepancies and problems that we already saw. Okay, in the next step, I said in 1.3 that we applied the principle of correct neglect, and I pointed out a paper here that you can read more about this principle. There are many processes. These are the processes we had considered in the original European project. These were the agricultural management. We had planting, rotation, irrigation, fertilization, about 43 different management plans across Europe and Black Sea. We considered point sources. Usually I do consider point sources because then you can account for water treatment plants, springs, if you are in mountainous region and so on, both inputs and outputs. There were no water transfer in this particular watershed, but there were dams and reservoirs, there were potholes and small water storages. In step 1.4, I plotted the river connectivity. I showed you last time how to do this. But in general, the river connectivity is very good. I mean, all the rivers are flowing in the right direction and then exiting the watershed here. So this looks good. The next step was to make observation files. And then I showed you a program that you can use to make observation files. Here are my original files. I have about 11 discharge and about 5 nitrate stations. So I have prepared the initial files here very nicely. I divided this into calibration and validation parts, and usually what I do is I take 2/3 of the data for calibration, and I take about 1/3 of it approximately for validation, and around 2/3 I try to find the breakpoint in such a way that the average and the standard deviation of the two parts of the data are more or less similar, as I explained before, and so I find the cut-off point between calibration and validation for every station. Then I divided the data into calibration and validation, and then I used that program that I showed you last time to give me the SWAT-CUP input file for observation and so on. So this I have done before, and the next step is divide the observation. Okay, I have already covered that. I did that, and then plot the calibration and validation data to make sure that visually there are no anomalies and that they are more or less the same. And then the next step was to produce a pre-calibration simulation. So that is what we are going to do next. All right, so let's go back to our Danube project and start editing the input files. Initially, when you open the project, a new project, this is what you get. I have put some parameters here for your convenience, so you can just use them. It doesn't mean that you have to calibrate for only these parameters. So initially, I just want to run the initial model. So for that, I set the number of parameters to 1, the number of simulations to 1. And then I take a parameter which has no really influence in my project, and this is a parameter in Basin, and I really am not sure what it is, but I copy it here, and initially its value is 0, so I do a value change of this parameter from 0 to 0, which does not change anything. The next file is this SWAT edit definition file. Here I have to give the starting and the ending simulation, which is both of them 1 at this point. Then file CIO. File CIO, my calibration begins, my observed data begins in 1973, but I have 3 years of warm-up period down here. So I have to start my beginning year of simulation is 1970, and my calibration data for discharge ends in 2003. So I have 34 years of data, which goes from 1970 to 2003, right? That's 34 years of data. So that's all I have to change here. Let's not worry about the rest of this file, just to make sure that I have 3 years of warm-up period and that my simulation is monthly 0, is monthly here. Absolute file values, the parameter values, these are the value ranges given by SWAT, and SWAT edit does not allow parameters beyond these ranges to be inputted into the SWAT file. So if you have this parameter is larger than 5,000, it'll put it to 5,000, and if it's below 0, it'll put it to 0. So this is, you can edit this file. If the range of parameters is not adequate for your region, then you can change it here. Next is the observation. So I have reach data, so I activate the reach here, and only the file reach gets activated. That means that's all I have to work with. Now, initially, I would like to simulate the discharge. I have, as I said, 11 discharge stations, and these are the files that I have created with the program that I showed you last time, and it includes my 11 stations. Next is how do I extract. The first thing is to give the name of the files that I need to extract data from, and these are the names of the variables and also the names of the files, and when the data is extracted, it will go into these files. Now I don't want to do nitrate at this point, so I can just simply delete nitrate. Then I go to definition file. Here it says I have, it's quite self-explanatory really. I have the output.ch, That's my SWAT output file. Initially, I have one variable, so I can set this to 1. And my discharge is in column number 7. You can count this. It's really just count the columns. It's either 6 or 7 or 8, maybe, depending on the SWAT version. You can just count it. And then the number of subbasins is 54, and I have the 11 discharge file, and these are the number of subbasins from which I have observed discharge. And this has to be in increasing order. So I can just delete this for now because I only want to do discharge. So if you have 3, then you just add another two rows here to account for your third variable. So it's simple as that. And my simulation goes from 1973, yes, but it ends in 2003. So I edit this, and 2 here means monthly. Okay, and then I go down to objective function. Objective function, you can extract more variables that you want to use in the objective function. So that's why you have two different files for this. So here I'm including all 11 variables. I choose number 5, which is nice SWAT-CUP, as my objective function. This is the weight for multi-objective. Don't worry about this now. And this is the threshold for behavioral objective. Don't worry about that now either. And the last row just says if you're using modified nice SWAT-CUP, then this is the power. So you can consult the manual for the meaning of this. And then I have all of my outlets here. So the first one is from number 6. This is the weight of this variable. This is the constant flow separation. As you notice, I have removed the dynamic separation because that really caused problems and it wasn't working. This base flow separation programs, there are different programs, and anyhow, they're not working very properly, so I removed it. So if you have constant separation signal, then this is the weight of the below and the weight of the above threshold. Again, you can consult the manual for this. I have covered this many times before. And this is a percentage of error in your measurement. Usually our measurements have quite a bit of error. 10% is the value that I came up with from the different literature. If you have sediment, nitrate, this could be much more. For sediment, you could go up to 50% really, because the measurement error in sediment is quite high. And these are the number of data points that I have down here. So I have 200 data points. And if there are missing data, then of course you begin from somewhere wherever that you have data. I have again covered this, and you can consult the manual for the implementation of missing data. So that's the same for every other variable down here. And then the next file is the variable file name. And initially, again, I can remove nitrate because I only have flow at this point. That's really all there is. It's quite simple. Once you use the program to create your observation files, it is a very simple input files. But unfortunately, many people make a lot of mistakes in preparing these few simple input files. Now I save everything at this point. The only other thing I need to check here is that the executable files. The executable files are the engine of the program. I have covered this before. So the only thing that's interesting here to check is the extraction. I have to make sure that I am extracting from the reach file, which is checked. That's fine. And these are the no observation files. Let's not worry about these right now. So I uncheck this. Save again. And the rest, I don't need to change anything. So at the end, I save everything. And I close everything. And I make sure the parallel processing is off, which it is. and then I just make one simulation. So run the pre-processing, okay, and run the program here. So that was too quick. So there is something didn't go right. So if I check this, what happened? SWAT edit worked. When it came to SWAT, it says SWAT is not recognized as an internal or external command. So that's because SWAT-CUP does not carry SWAT anymore, so you have to copy your own SWAT into your SWAT-CUP project folder. So let me just quickly do that. So SWAT is installed in my computer and probably in yours in the SWAT folder, in the C SWAT folder, arg SWAT. And if you go down here, you will find different versions of compiled executable SWATs, the 32-bit and then 64-bit. And there is a debug version and a release version. The debug version is a much larger compiled program, so it's 17 megabytes. So you use debug only if SWAT crashes and you want to find out where the problem is. It would be good to run the debug once and see where the problem is. But usually it's the release that we need. So I copy this and bring it into my SWAT-CUP folder, and I change the name to SWAT-XA. Now, for some people, this appears that this doesn't work. That's because moving executable file is a bit tricky, so you need to have the administrative right sometimes to do this. So make sure that you're able to copy this file here. So I go back to my project and I repeat the steps again. So pre-processing, working, and then I go to run. So SWAT-CUP, so this time SWAT is running, so that's fine. And then for the last step, I have to run post-processing, and I have different post-processing. This is single objective post, which is what we need right now. Then I have behavioral, and I have multi-objective, single, and multi for all of them. And then there is no observation post-processing. So we are just concerned right now with single objective post. So I run this. And when you're just doing the one simulation, this program, the new parameter program, will not work because with one simulation it just cannot give you anything. So it gives an error, but you can ignore that error. So and then, so at this point you can close some of these, so you can go to your output and visualize the 95 PPU. So that's what we have. So for all the 11 outlets, I get the initial simulation. So it doesn't seem to look so bad. And sometimes I have I'm overestimating the peaks here. Here, underestimating the base flow. For the next outlet, again, underestimating the base. For the next outlet, looks quite good. The dynamic is always quite nice, and and for number 21, underestimating the peak and the base and so on, the peak actually. And then for the next one, similarly, always underestimating the base, and the peak here, and so on. So this is what my initial simulation looks like. I think I can calibrate, at least for some of the outlets. I can do a much better job, I'm sure, by changing the parameters. Now, I spent quite a bit of time on pre-calibration things that you have to do. It's really worth it to spend some time to make sure that you have the right model. The worst thing is to try to calibrate inadequate model. So you cannot just build the model and then hope to fix it by calibration. Calibration does not fix it. For calibration, you need to have initially some meaningful calibration simulation results, and then you can make that a little bit better by adjusting the parameters. So you should not count on calibration to cover the missing processes and so on and so forth. If you have important processes missing, even if you get a good result, your parameters will be really meaningless. The only other thing we can look here is the summary stat, and the summary stat gives you statistics of quite different statistics, and the P factor and R factor don't mean anything here for the one simulation. The R squared is not bad, as we saw the dynamic was quite good, but the nice Sutcliffe is not so good. We have quite a few negative numbers, which is which means we better not simulate that we simulate. And then you have the other statistics, PR squared. These I have explained before, so I won't spend too much time here. So my initial simulation tells me that it's okay. I can go ahead and calibrate this model. I'm going to save this iteration and call it just call it 0 initial. 0 because I want to keep my different iterations in order, so I just call it 0 initial. So this is okay. Now the next thing I want to do, as you saw before, that we were in snow. I mean, the river started from the snow mountains, so I need to then add elevation band, which I have already done when I was building the ArcSWAT project. And to check that, you go to any of the sub files. You can see that I have added elevation band, but TLAPS and PLAPS have not been fitted yet. There is no value for them. So the first thing I need to do is to do the TLAPS and PLAPS, because I'm in a mountainous region. You also notice that I have added, I always do add point sources to every subbasin. This is very useful when it comes to calibrating the base flow, because the base flow, quite a bit of base flow comes from springs and water inputs into the system from water treatment plant and so on. And there is no parameter for that. You just have to give the right discharge from these sources. All right, so let me go here, and I add now TLAPS and PLAPS, and I can easily just grab these parameters here and copy them here. If I don't know anything from this subbasin, it's okay, I think, to start with these numbers. For PLAPS 0 to 100 millimeter, and for TLAPS from -8 to -4. So now I have 2 parameters, and I would, at this point, usually I do 64 simulations. That's because I use my parallel processing, and I have 8 CPUs, and I run about 8 simulation in each CPU. So I found that to be sufficient at this point. So I have 2 parameters. I want to do 64 simulation. I can also fix that here, say that beginning and the ending is from 1 to 64. And then that's really all I have to do. I save all, I close all. You should always do that. And pre-processing and run. Now the parallel processing is active here, so every one of these windows show a different CPU, and I can see this is simulation from 1 to 8 goes here, and then from 9 to whatever goes there. So you can visualize that here. You can see that 100% of my CPU is engaged, so that means I'm really using full power of my laptop. If I was running only one simulation, then a fraction of my 100% would be used. So that's why this is much faster. If you have a large project and you're making many simulations, it would be much faster to use the parallel processing. Okay, the run is finished. Now I can run the post-processing, and I can visualize the simulation. Well, so it appears that the values for PLAPS that I gave were very much for this region. Let me look at the dotted plot. Now, the dotted plots, we can learn quite a bit from this. One is that it shows a very nice trend for my PLAPS. So as the value of PLAPS here increases, my objective function here, SWAT-CUP, decreases sharply. So the value of the PLAPS should be around 0, because if I deviate from 0, I will be going down in my SWAT-CUP. And also, TLAPS is quite random, so that means it's really not a sensitive parameter. So I can also check that if I run the sensitivity, global sensitivity here. So you can see the same thing, right? You can see that PLAPS has a T-stat of -32, TLAPS has 0.3. So here we would like to have a large value in terms of absolute value, should be very large, and here it should be very small. Actually it should be really 0. So this is 0 and this is -32. So stat tells me that PLAPS is a very sensitive parameter. So the value that I gave was really too large. And I can also verify that by going to our new parameter. So new parameter tells me I should have a range of -50 to 51 for PLAPS. So it tremendously shifted the value, which initially was from 0 to 100 to even negative values. But my TLAPS is from -8 to -5. That's about what it was before. Because it's not a sensitive parameter, then this really doesn't mean very much at this point if the parameter is not sensitive. All right, so what I'm going to do is I'm going to save again this iteration, and I will call it 1. Just call it labs. That means I'm calibrating the labs parameters. 1 labs. Okay. You can look at the summary stat. I should have an extremely large R factor, as you can see here. So I do another simulation. I will have this then to be around 0. So I would go from 0 to 0. Probably to 1. Put it 0 to 1. And this I can already reduce to go to -7 to -5, because for every kilometer you lose about 6 degrees Celsius. So between -5 and -7 should be good. I save everything again, I close everything, and I do another simulation. Alright, this iteration is finished, so I can run the post-processing again and look at my results. So it looks a bit better than before, although still seems like 1 was quite high everywhere. So, but it's probably okay. I think my best parameter is 0.11. So what I do is I take this simulation. I'm not really hard calibrating here, so this is quite okay. So I save this iteration as 2 labs, okay, and then I fix the 2 labs parameters, right? We talked about this quite a bit before. So to do that, I can go to summary stat, and here it says best simulation number is number 19, right? So this file is now useful here. So what I have to do is start from simulation 19 and end to simulation 19, and what this does is only put the parameter set number 19 into my SWAT files. So I then shut down this parallel processing, and all I have to do at this point is not to run pre-processing because I don't want to sample again. I just have to run once. So when I run, you see that parameter set number 19 is only going to run, and that's that. So I have now parameter set number 19 in my files, and okay, so I have now parameter set number 19, which was the best parameter, into the SWAT files. So why is that? Now the question is, why did the PLAPS was so small? The reason for that is that if you look at my climate stations, I have quite a bit of climate stations in my watershed. So I have stations on the mountains, I have stations on the flat areas. So because of that, I don't need to adjust, I don't need to have much PLAPS because I already have stations on the mountains. So if I only had 1 or 2 stations down below here, then I had to increase the rainfall as I go up. So my PLAPS would be a much higher value. But right now I have stations here, and I don't want to increase it even more, right? For these stations, they're already measuring the right rainfall and snow. That's why, because I have many stations, TLAPS and PLAPS don't make too big of a difference. So I don't need to have a large PLAPS to account for that elevation. That's the reason. But because I'm in a snow area, the next thing I want to do is to fit my snow parameters. And for that, if I go to RINF, so this is done, push this down, and I take my snow parameters. They're all conveniently here. So I take the snow parameters, get rid of this line here. And I can use these initial values. They are usually okay, but now I have 5 parameters. Now again, I said before, and I said again here, you cannot fit snow parameters and lapses and everything all together, right? First TLAPS and PLAPS, then snow parameters. So I have 5 parameters. And for this, I usually make, because we have more parameters, I have to make more than 64 simulations. I usually make around 320 simulations. For my 8 CPUs, this would be about 40 simulations per CPU. So I save this. I go back to this file and set this to 1 and 320. Save everything. And all I have to do now is to run the program. All right, our simulation of snow parameters is finished. So let's run the post-processing. Okay, and let's look at our output results. So that's what we get after adjusting snow parameters. So let me just go to summary stat. And let's compare the summary stat now with summary stat at the beginning with my initial simulation. My initial simulation, the overall objective function was 0.029. It was negative, and many of my stations were negative in SWAT-CUP. Now the objective function overall is positive. It's not that great. It's 0.19, but it's positive. And most of my stations have positive SWAT-CUP, except for 2 of them. So the PLAPS parameters and the snow parameters did make some difference, but not a huge difference as expected, because I have stations all over the place, including in high mountains. So the next thing I want to do is now to parameterize each station and try to calibrate by using appropriate parameters. And that is something that we do in the next video. Thank you for watching.